Hi everyone, welcome back to ChemHelp ASAP. In this problem set video, we are going to be talking about intermolecular forces. Now we will start with identifying molecules as polar or nonpolar. Then we will practice identifying the different types of intermolecular forces. We will introduce the rule like dissolves like, and we will use those intermolecular forces to make predictions. And then we're going to finish out this problem set with some density problems. Let's get started. Let's use geometry to determine if a molecule is polar or nonpolar. So here is my table summarizing geometries and polarity. Ozone is formed when 3 oxygen atoms bond. It has a bent shape. Is ozone polar or nonpolar? This is a little bit of a trick question. So if we go to our shapes, here is bent, and we can see that it is polar. However, how is ozone formed? We have 3 oxygen atoms that are bonded together. Is there going to be a difference in electronegativity? No, there is not, because we have 3 identical atoms bonded to each other. It does not matter what shape it takes, it is going to be a non-polar molecule because it does not have any polar bonds. Methane is a common gas. It has a tetrahedral shape. Is methane polar or nonpolar? Finding tetrahedral, here we go. That is a nonpolar molecule. Do we have polar bonds? Yes, because we have carbon bonded to hydrogen. They're not the same atom. So methane will be a nonpolar molecule based on its shape. Once we know if a molecule is polar or nonpolar, we can predict the dominant intermolecular force. Both NH3 and PH3 are trigonal pyramidal. Do they have the same dominant intermolecular force? Okay, so let's find trigonal pyramidal. Here it is. That means we have 2 polar molecules. So polar molecules are not going to be induced dipole. They are either going to be dipole or they could possibly be hydrogen bonding. Looking at ammonia, or NH3, I see that I have a nitrogen bonded to hydrogen. That means that hydrogen bonding is going to be our dominant force for ammonia, or NH3. However, PH3, while it does have hydrogens, they're bonded to a phosphorus, which does not participate in hydrogen bonding. So its dominant intermolecular force will simply be dipole. So they do not have the same dominant intermolecular force, even though their structures are very similar. What is the dominant intermolecular force in the following molecules? And we have bromine and hydrobromic acid. Again, molecules that look very similar. Looking at bromine, that is simply one bromine atom bonded to another. That is going to be a nonpolar molecule. There's no difference in electronegativity. So the dominant intermolecular force in bromine gas is induced dipole. What about hydrobromic acid? It looks like maybe it could have hydrogen bonding, but we don't have a hydrogen bonded to a fluorine, oxygen, or nitrogen. But it is a polar molecule because there will be a difference in electronegativity between hydrogen and bromine. So hydrobromic acid will have dipole. Again, you can see even though these structures are very similar, they have very dissimilar intermolecular forces. Let's use our intermolecular forces to predict some properties of different molecules. Which molecule would you expect to have a lower freezing point? Ammonia, which is trigonal pyramidal, or NCl3, which is also trigonal pyramidal? We have seen ammonia before. This has hydrogen bonding. What about our NCl3? That does not have hydrogen bonding. However, it is a polar molecule. So we have the difference between hydrogen bonding in ammonia and dipole in NCl3. If we're looking for a lower freezing point, that means we want the weaker of the 2 intermolecular forces. That means NCl3 is going to have the lower freezing point. Is O2 or hydrofluoric acid more viscous? Let's think about intermolecular forces. O2, of course, is just one oxygen bonded to another. That is a nonpolar bond, so O2 is going to have induced dipole. Remember, that is the weakest of the intermolecular forces. What about hydrofluoric acid? Could it possibly have hydrogen bonding? Yes, it does, because fluorine is one of our special atoms. So in this case, we are comparing our weakest intermolecular force to our strongest intermolecular force. Now, in terms of which one is more viscous, the stronger the intermolecular force is, the more viscous the substance. So our hydrofluoric acid is going to be more viscous than our oxygen. Now let's use our polar, nonpolar predictions in a little bit different way. Will gasoline, which is nonpolar, dissolve in methanol, which is bent? If two substances are going to form a solution, they either must both be polar or both be nonpolar. We are told that methanol is bent. If I go to my geometry and find bent, that is a polar molecule. So I have gasoline, which is a nonpolar solvent, trying to dissolve methanol, which is a polar solute, so no, they will not dissolve. Our question reads, an unknown metal cube has a volume of 30 centimeters cubed. When the cube is weighed, it has a mass of 580 grams, and we need to identify the unknown metal. Now we are given a hint. 1 milliliter is the same as a centimeter cubed. Here we have a table of different substances and their densities. Let's calculate the density of this unknown metal. So density is simply mass over volume. We know the mass, that's 580 grams, and we were given the volume as 30 centimeters cubed. Let's plug that into our equation. Here we go. But we have a little bit of a problem. In our table, our densities are given in grams per milliliter, not grams per centimeter cubed. But our hint told us that 1 milliliter equals 1 centimeter cube. So let's set up a quick conversion. Here we go. Our centimeters cubed cancels. Now we have milliliters. So our density is 19.3 grams per milliliter. Let's see if we can find this in our table. There it is. Our unknown metal is gold. Next question. If you have 1.25 kilograms of mercury, how many liters of mercury do you have? Mercury is an unusual metal. At room temperature, it is a liquid. So let's find mercury on our table. Here it is right here. Now remember, this 13.55 is measured in grams per milliliter. So it looks like we're going to have to do some unit conversion. Starting with our 1.25 kilograms of mercury, let's first convert this to grams so we can use our density. So here is our kilograms to gram. Now we can use our density to figure out our volume. So here is our density of mercury. Again, I got this from the table. Make sure your units cancel. You notice I put my 13.55 grams in the denominator. That gets us to milliliters of mercury. But our problem asked us for liters, so we have one more conversion. That is simply milliliters to liters. And now we can do our math. So that gives us 0.0922 liters of mercury. A bottle of glycerin has a mass of 500 grams. How many milliliters of glycerin is in the bottle? Let's find glycerin in our table. Here we go. Remember again your units. Okay, starting with our 500 grams of glycerin, we can use our density here. We're converting from grams to milliliters, and we get 397 milliliters of glycerin. The place where most students get tripped up in these problems is not paying attention to the units of the density. So just make sure you're always watching those units. I hope working these problems together has helped you, and thanks so much for watching.